So I have only like 33 slides. So initially, a few slides, mostly administrative ones, and in the end, a few like summary slides are also less relevant to the propensity course themselves. CTSI BERT, so it will be Biostatistics, Epidemiology, and Research Design. This is our group, which is partially funded by CTSI. Director is Dr. Huang from UWM, and statistical support is provided through three different biostatistics groups. One group, which would be Division of Biostatistics from UWM. Another group is our group, like Biostatistics Consulting Services from Division of Biostatistics. And another group of statisticians, CAPS, from the Department of Medicine at the MCW. So which assistance you can get? So if you apply for small mini grants, so you get like 4 to 6 hours of biostatistical consulting help. So during these hours, you can typically discuss your project aim, study design, maybe review and confirm what data analysis need to be used. You can do like some sample size calculations, some basic preliminary data analysis. So essentially what we can do realistically will be like around 5 hours. And you can submit applications for grant proposals for these mini awards through this website page. So typically these 4 to 6 hours is not enough to do any like substantial data analysis. So potentially you can also get assistance from our Division of Biostatistics, from our consulting group. So it's typically what's going beyond this basic 4 to 6 hours. So it will be some more comprehensive data analysis, grant writing, proposal preparations, purpose data management, statistical modeling, design of clinical trials, randomization. So whatever goes beyond like 4 to 6 hours. What our rates are right now. So if you apply for biostatistics consulting services and you do not belong to the Department of Surgery, Orthopedic Surgery, PM&R, further pharmacy, or if you're not from the Division of Pediatric Emergency Medicine and Hematology Oncology, so then rates are 180 hours for a PhD and a little more than 100 hours for MS biostatisticians. What will be covered in our talk today? So first, we will review main concepts about causal inference and potential outcomes. We will talk about population, sample, and we will discuss differences between randomized clinical trials and observational studies, and how propensity scores can be used with observational studies. So propensity scores typically used in different ways, how we can adjust for confounding in observational studies. And we will discuss 4 possible approaches to the inverse probability treatment weighting. It will be first approach. It's typically the most popular approach. And then a couple of other approaches of use propensity scores. It will be including propensity score as a covariate. We will use propensity scores for post-stratification and propensity scores for matching. We will discuss assumptions which come with propensity scores, and we will summarize quickly our talk today. Review of potential outcomes. So let's just consider 4 patients, and we just enumerate them like A through D. And each of these patients can be treated or not treated, right? So we essentially consider like only 2 groups of patients, treated or not treated. Not groups, maybe it's not correct to say groups, because groups typically mean that we have different patients in groups, right? But 2 different conditions, right? Treated and untreated. So, and each patient can be treated or untreated. So, and this is where we get these potential outcomes, because in real life settings, so patients either treated or not treated. So, and for example, if you treated the patient, so this, we cannot observe an outcome and patients would not be untreated and other way around. But potentially there are two possible outcomes if patient is treated and then patient is not treated. So in this case, we these two potential outcomes, we can calculate difference between these two outcomes, and that will be a treatment effect. So, and here we calculate the treatment effect for these four patients. So for first one, it will be like 2 minus 1, right? Treated versus untreated. So it will be 1. So in similar way, we can calculate treatment effects for each of the patients. But remember, these are not observable because each patient can be either treated or not treated. So these treatment effects can be calculated potentially, right? Potentially again for each patient. And if we average all of these outcomes across all patients in our population, then we obtain so-called averaged treatment effect. Averaged treatment effect, ATE, is a special effect, a special case of causal effect. So in general, we can talk about averaged causal effect, because causal effect, it's a generalization of a treatment effect overall. Because when we're talking about the treatment effect, so in this case, we have just typically two possibilities, treated or untreated, right? But more generally, we can talk about a like continuous treatment. We can talk about different doses, right? We can talk about different multiple treatment choices. This is where it gets more complicated. But in a very simple scenario, we have just treated and untreated, just binary binary exposure variable. Oops, where I was. Okay, going for the next slide. Okay, so a note on a population and a sample. Typically, when we design a study, we determine what our population is, what patient population we're interested in. And this patient population is typically determined by an inclusion and exclusion criteria. So you say like we want adult patients, right, 18 plus, or we want specific sex, or we want some comorbidities, some specific diagnosis. So this is how we typically determine our population. And we typically exclude from this population, when we use exclusion criteria, some specific situations we are not interested in. So it's why it's inclusion and exclusion criteria. The next step, typically, we select a sample, and this sample should be representative of overall population, which we determine by our inclusion and exclusion criteria. But this is where the challenge comes in, because, for example, if you have a like clinical trial, right? So it's difficult to obtain, random sample from our population. That's why in many cases you have to proceed with so-called sample of convenience. So you recruit in a clinical trial wherever you can, which actually belong to this specific inclusion and exclusion criteria. Populations. So populations can be big, right? Like thousands and millions of patients, right? Potential patients. And you can define population to be small, some finite populations. For our talk, for simplicity, we will consider a very simple finite population of 8 patients. Okay. So, and we would assume that our population, since it's only 8 patients, is fully included in our sample. Like in survey data analysis, this type of sampling, when everyone is surveyed, is referred as census, right? So census, it means like your sample consists of 100% of your population. So everyone is included in your sample. This is just out of convenience. We consider a specific case. But in general, populations are much larger than just 8 patients. Okay. Next slide. Yeah, this is a sample. This is a sample to consider. So in this case, we have not 4 patients right now, but we have 8 patients. 8 patients. And we assume these 8 patients represent our big overall population. Not represent, it's all our population. And all patients are selected in our sample. So what happens? We randomize these patients in a clinical trial. So what do? We randomize patients between 2 groups, treated and untreated, right? Placebo, untreated, it's like a placebo group, right? Treated, this is the intervention group. And we observe only one of 2 potential outcomes. For example, for patient A, this patient A was randomized into treatment group. So in this case, we observe the outcome in one condition when patient is treated. But the other outcome when patient is not treated is not observed. Okay. So, and certainly when they calculate like treatment effect for this patient, it's also not observed, right? It's unobservable. For second patient was randomized into untreated group. So we observe untreated outcome. So what else we know for across all of these patients? We also know their ages, right? But the nice part about randomization is that all these are the variables which we have, which we measure, which are measurable in our patients. They should be approximately, they should have approximately the same distribution between two groups, treated and untreated. It's a nice part about randomization. So again, we will continue with talking about this RCT, randomized controlled clinical trial. As I mentioned, okay. As I mentioned, in this group, we will have 8 patients, and this is our population and the sample at the same time. How treatment effect can be evaluated? So typically, in many cases, we just consider average in treated group, sample average in treated group, and sample average in untreated group. And we consider difference between these two sample averages. So that will be, we will refer to it as a sample difference for simplicity, okay? So sample difference estimates our unknown average treatment effect, okay? Because average treatment effect can be only estimated, we don't know it exactly. Even though our population and sample is the same thing, right? So we evaluating every patient in our population, but we are not evaluating the same patient under both conditions. Only one of these conditions can be measurable. Second point, average treatment effect is a population parameter, and it's only a special effect, a special case of averaged causal effect. So since in this talk, we will mostly be discussing two groups. So that's why in this specific case, it's a binary treatment, like yes, no, treatment applied or not applied. So in this case, treatment effect, average treatment effect is the same as average causal effect, because we would like to establish causal effect from treatment to the outcome. In this case, causal diagram is very simple. So in this case, we have randomized treatment and we predict our outcome. So in this case, we have a causal relationship. So if you would calculate difference between two sample averages and treated and untreated group, so the effect is estimated, causal effect is estimated as 1.3. So in this case, we're talking about randomized clinical trial, right? 1.3. But if you go back to our sample, so if you would calculate average for the whole column, our average would be around 1.7. And this is what we have. 1.71, it's our true average treatment effect, true ATE. This is what we want to estimate. This is our population parameter. So that's why I consider a population of only 8 subjects, right? Because I could calculate my ATE in this hypothetical example. So, but when we consider just average between treated and untreated, so it's a different number. It's an estimate. An estimate is 1.3 in this case. As I mentioned, since we do randomization, distribution of covariates should be approximately the same between these two groups. And if you would just look at those who were treated, so patients are treated at ages are like 22, 44, 66, 88. If you consider average across these 4, our average age would be 55 years in the treated group. In the group which was not treated, untreated group, average age is 66. So similar. Of course, they're different. Every time, we will get slightly different numbers, but yeah, they're similar. Let's consider an observational study. In observational studies, we cannot randomize patients between groups. And in observational studies, there is some self-selection process because a decision whether to being treated or not treated depends on a lot of different circumstances, right? Depends on patient beliefs, whatever advertisement patient saw, uh, on a physician, so on a lot of different things, on insurance. And so that's why in the end, we have different distributions of patients between like treated and untreated groups. And certainly if distributions of patients differ in terms of, for example, their age or some other confounding variables, we would expect different response to treatment, right? So I changed the same example like I had before, but I changed random assignments to non-random assignments. So right now I have more younger patients, right, in the treated group, more younger patients in treated group, and in untreated group, more older patients. So, but causal effect continues to be exactly the same. So what changed is that we do not have randomization. We have only like self-selection into the treated group. So yeah, I already mentioned that. So treatments are not randomly assigned to patients, but self-selected. So in this case, our causal diagram is different. Because in this case, in addition to the treatment indicator and outcome, we also get a confounding variable, age. So we consider just one age at this point. So age potentially can affect both an treatment indicator and an outcome. Right. So in this case, you remember, like from the randomized clinical trial from RCT, our sample difference between two treatment groups was like 1.3, which was somewhat close to 1.7. But if you consider observational study, so this sample difference between two means in treated and untreated group is much lower, is 0.575. So certainly this is just an artificial example, but I chose this example to illustrate overall issue, what is happening. Because if we have randomization between two groups, our observed like sample difference between two sample means would be would be an unbiased estimator of average treatment effect. But when we have a self-selection, when we have observational study, many biases come in. And that's why just sample difference between sample means would be a biased estimator. And this bias can be also observed in differences between distributions of ages between treated and untreated patients. So in this case, average age in treated patients will be 41 years of age, and between untreated is close to 80. So difference like more than 30 years. So, and in this case, we can calculate bias, observed bias, not true bias, but observed bias. So, and observed bias in the RCT, it will be negative 41. It's not really observed bias. It's maybe not the correct word, because like 171, it's like our true treatment effect is not observed as well. Yeah, so it's not the correct term I used here. But let's say it's like a bias, right? So here we see like negative 41, but here we have negative 1.1. So certainly they are much further away when you're talking about observational study. And then we compare like the difference between sample mean, between average age between treated and untreated. It will be 11 years in RCT example, and in observational study example, it will be almost 40 years. How we can reduce these imbalances? So, and this is where propensity scores are helpful. So, and now we consider a little bit more complicated scenario when we have two confounding variables, age and sex. So what propensity scores do? Propensity scores allow you to break this type of paths. So paths which go from treatment to the outcome. So they close so-called backdoor paths from attributed to several confounders. So what do we do? So we see like age affects our self-selection process and sex affects our self-selection process. What we assume is that there is like another component here, which can be called a propensity score, which is unobservable, but it exists, right? So in this case, this propensity score is influenced by age and sex, and it determines probability that a patient selects treatment as opposed to being not treated. So we can say that propensity score accumulates the effects of multiple confounders into a single quantity. How to calculate propensity score? We will consider how to use it later, but how to calculate propensity score. And we are going back to like single example, to an example with a single confounder. So again, we have two treatments, and propensity score in this specific example, it will be probability of being treated. It will be just single number between 0 and 1%. In our example, when we observe our data, in observational study, we can use a scatter plot, right, to show dependence between treated status, treated versus untreated. So treated would be 1, and untreated would be 0, and age. So we can just prepare this scatter plot. So again, like 4 patients are treated, younger patients. This is where we have these solid circles, and untreated are over here. So certainly you see a shift, right? So untreated patients are older and treated patients are younger. In RCT, picture is different. So untreated and treated patients, due to randomization, they have approximately the same ages. But we see imbalance over here in observational study. Next step. So when we observe this imbalance, then we can model this imbalance. And for binary outcomes, propensity score is typically modeled using logistic regression. In logistic regression model, they use age as a predictor for the probability of being treated. And this is a statistical model for logistic regression. These two parameters, beta 0 and beta 1, intercept and slope in logistic regression, need to be estimated. And we estimate these parameters on the basis of data we observe. So in this example for observational study, we use only 8 points, sample size of 8, to estimate these two unknown parameters, beta 0 and beta 1. But when we estimate them, we can produce this curve. So that will be predicted probabilities of being treated. And probability of being treated certainly higher for younger patients and lower for older patients. Then we're talking about RCT, randomized clinical trial. So we can also potentially fit with logistic regression, but whatever association we observe just happens by chance, because we know by default it's a randomized assignment, it's impartial assignment of treatments. So yeah, we typically, if we know that we're talking about a randomized clinical trial, we typically don't want to do that. Because yeah, as I mentioned, it's by design, so ages should be independent of treatment in randomized clinical trial. In observational study, dependence might exist, so that's why we fitted this curve. So when we fitted logistic regression, so we estimated, as I mentioned, unknown parameters, beta 0 and beta 1. And when we plug in these unknown estimated parameters into our formula for logistic regression, then for each patient, we plug in patient-specific age and we can calculate probability of being treated. Maybe I should remove I from here because it's just estimating probability of being treated. Then for each patient on the basis of his or her age, we can calculate P sub I. So that will be propensity of being treated. And I plotted these propensities with these triangles over here. Now, back to my example. Observational study, cell selection into the treatment group. And here I added column of propensities. So I just applied the formula, which I just listed on previous slide. How propensity scores can be used? There are several ways how these propensity scores can be used, and I listed them at my initial slide. Inverse probability of treatment weighting, then stratification, inclusion as a covariate, and matching. These two possible ways how propensity scores can be used to adjust for the confounding effect. First, we will consider inverse probability treatment weighting. So essentially what weighting does, weighting creates like a new hypothetical situation, new hypothetical world, where treatment are randomly assigned to patients independently of confounding variables. So if you remember, like initially, we had this picture, right? So because age and sex, they predict this propensity score, and propensity score predicts the probability that a patient gets one or another treatment. So, and when we apply weighting to our data, to our observed data, and our observed data will be age, sex, randomized assignment, and treatment. So in this case, distribution of ages will be approximately the same, and distribution of sexes and distribution of outcomes will be approximately the same between treated and untreated patients. And this is what is happening in the randomized clinical trial. So essentially, when they apply specific weights, we are essentially mimicking a randomized clinical trial. This is what propensity score does. So that's why I put here like W. If you consider weighted versions of, for example, of weighted sample mean, right, in one group and weighted sample mean in another group, they should be approximately similar when we apply weights based on propensity scores. How these weights should be calculated? So essentially, weights are equal to inverse probability of receiving a treatment. The person of a treatment the person actually received. So because we have two groups, in the group of treated patients, we just have inverse probability of treatment. So it will be 1 over P sub I. That will be our weights in the treatment group. If you consider group of untreated patients, in this case, that will be probability, the weight will be 1 over probability of not being treated, which means 1 over probability, 1 minus P sub I, because probability of being treated is P sub I, probability of not being treated, 1 minus P sub I. So, and then we have like multiple treatment groups. So in this case, we have our weights will be 1 over probability of receive a treatment that this patient actually received. Okay. And in this slide, I calculated these probabilities for each patient. So what do we see here is that if a patient received a treatment that this patient is supposed to receive, right, and its probability is high, then weight doesn't change. So it's approximately equal to 1, right? But only for the patients in this, gray zone. So in this case, if they could get a treatment or could not get a treatment. So in this case, this patient get a higher weight, higher weight. And I do not have examples here. Then patient is highly unlikely to receive a treatment, but somehow this patient receives a treatment. It's like so-called hard to reach populations, right? In this case, this patient will get really, really high weight, okay? Now, so when we calculated these weights, then all our analysis should be weighted after that. Analysis should be weighted on these weights. For example, when we want to estimate average treatment effect, AT, right? So in this case, we should consider difference between weighted averages. So if we have, for example, like 4 patients, right, in the treated group, so we would consider not just a simple average of the outcomes within treated group, but weighted average. So, and this is what I wrote over here. So that will be weighted average of the outcome in the treated group. And then we have weighted average of the outcome in untreated group. So, and difference between weighted averages would be an estimate of the average treatment effect. So in a similar manner, we can also calculate weighted averages of ages for treated and untreated patients. And what is interesting is that when we use inverse probability weighting, in this case, our weighted ages will be approximately the same between 2 different groups. And then propensity score is used for inverse probability weighting. Then so-called love plots are created. I did not present it here. Maybe it will be presented well, at our next presentation in December, because we will go deeper in propensity scores. But love plots essentially show that distributions after proper weighting, they will be approximately the same. Distributions of all confounding variables, approximately the same. And here I gave a little bit more details between unweighted and weighted analysis. So if unweighted analysis, so treatment effect was estimated as 0.57, then in weighted analysis, it will be 1.09. And you remember true effect, treatment effects for all 8 patients was 171. Then we consider unweighted means, it would be, again, 41 versus 79 years, high difference. And, when weights are applied, in this case, you get 48 versus 72. So it's a little bit closer, but not perfect. Typically, if we have large sample sizes, then we can calculate propensity scores more accurately. Because right now, when we have a sample size of 8, it's not sufficient to produce a reliable logistic regression model. Because it's still, our propensity score calculation is still based on a statistical model. But if we have 100 patients, 300 patients, so in this case, like we often have in observational studies, then we can more accurately calculate weights. And then weight analysis would lead to approximately similar distributions of ages and other confounding variables. So far, we just talked only about average treatment effect, right? But there are other causal effects which can be estimated. For example, average treatment effect in the treated population, and average treatment, no treatment effect. So it's average effect for the untreated population. So these two quantities can also potentially be estimated. And another possibility is that if propensity scores are used for matching, so in this case, suppose we get 1-to-1 matching, right? So this is typically applicable if you have small number of cases, those who have been treated, right? And plenty of controls. So in this case, we can run this logistic regression, calculate propensity scores for everyone, for all cases and for all controls, But for each case, we select like a single control with a similar propensity to receive a treatment. This is so-called matching on propensity score approach. But in this case, our population in our sample, in our matched sample, would be different because this population is not representative of all patient population. It's only representative of a small fraction, right, which are more likely to be treated. Surprisingly, propensity scores can also be used to analyze these other causal effects, which we just discussed, ATT, AUT, and matched population ATE. But weights are different now. Because you remember, like initially, like when we're dealing with just with average treatment effect, ATE, our weights were like 1 over propensity score and 1 over 1 minus propensity score, right? So this is what we considered in more details in our example. But when we consider other causal effects, other three, propensity score still can be used, and inverse probability weighing still can be used, but we have different formulas to calculate weights. Okay, so yeah, and these here we list these other possibilities. What assumptions we typically rely on when we deal with propensity scores? So first assumption, it's consistency. So it means that patients, if we observe outcome for a patient, whether treated or not treated, so this outcome is what it's supposed to be essentially. Because in real life settings, you know, patients can have some other medications, or they can, I don't know, they can drop, they can maybe not adhere to the treatment, right? So they can skip, you know, pills when they're supposed to take pills. So, and that's why consistency is important. Another thing is that exchangeability. So, which means that there are no unmeasured confounders. We assumed, like in our example, that we have just a single confounder H. But what if there are some other confounders which we did not include in our causal diagram? So this is not acceptable for propensity scores because in this case we can get invalid inference. And another one is a positivity. So each patient has a positive probability to receive each treatment. And in our case, there is a positive probability that each patient receive one treatment or another treatment. Sometimes this is not happening. For example, sometimes older patients are, or younger patients, I don't know, for example, cannot tolerate some specific treatments, right? So, and it's highly unlikely they will receive it. So probability is almost zero. So this is not an acceptable scenario for applying propensity scores. And another issue is that it might happen is that, and sometimes you cannot even fit a logistic regression model when they have a high separation between two groups. So for example, only older patients receive treatment and younger patients never receive treatment. So these type of situations are, in these type of situations, we cannot rely on propensity scores. Other possibilities how we can apply propensity scores. We can use propensity score as a covariate. So you know how to calculate propensity scores. We already discussed it. So, and then we just include it as a covariate in the regression model. Because in this regression model, if we exclude this propensity score, that will be just a t-test, just to sample t-test to compare two groups. But if you would add additional covariate, so it will be multiple linear regression. So in this case, we have just two predictors. One predictor will be treatment versus untreated. Another one is the magnitude, is the propensity score. Surprisingly, I just applied this multiple linear regression to our data, and we get treatment effect estimated as 1.78, which is really close to 171. But typically, across all of these possibilities which we consider, like inverse probability weighing, using the rest covariate, stratification, matching, inverse probability weighing is typically most reliable approach, most popular approach to use propensity scores. And there were like multiple simulation studies which supported that. Another possibility is to use propensity score for post-stratification. So in this case, we split our propensity score into different groups. So we aggregate our patients by propensity score. So if we have like thousands of patients, so in this case, you can create like 10% group, another 10% between like 11 to 20%. So we aggregate patients by their propensity. And then we essentially use proceed with stratified analysis, which means we would include strata variable as one of the predictors in our model. In this example, since I have only 8 patients, I consider just 2 groups, treated and untreated. So, and then, excuse me, not treated, untreated, propensity above 50% and below 50%, and included this binary variable in a linear regression model. So again, treatment effect is estimated as 111. Still much better than unadjusted analysis than the ignored effect of confounding. Another possibility is matching. As I mentioned, matching is useful if you have like a small number of cases and then you select controls. But the problem with matching is that we discard a lot of data, which can be potentially useful because, well, if you have like thousands and thousands of controls, it's typically not useful to use all of the controls, right? But if we reduce our sample size from, say, from 300 down to 10, for example, we have 10 cases and 10 controls, maybe you still lose some statistical power. So that's why you can consider other options like one-to-many matching. Okay, I'm reaching the end of my presentation. So here we have a brief summary of what we discussed. So we discussed what potential outcomes are and how we determine treatment effects, average treatment effects. We talked about randomized clinical trial. We talked about observational studies and how propensity scores can be used to adjust for imbalances associated with confounding variables. And then in the end, so we discussed 4 possibilities how propensity scores can be used for to adjust for the effect of confounding variables. Future lectures will be in December, January, and February. We will continue talking about causal inference. Next presentation will be on December 13th. So propensity scores in action. Dr. Aniko Zabo will be showing more details about propensity scores, and she will show an example how this is applied in real-life settings. And here we have references, and I'm done. Thank you for attending the talk.